Hello students, welcome back. Let us resume our discussion in section 2. We went through this problem, which I think is extremely important. Parts A and B always go together, and a single diagram completes both problems, like this. X-coordinate of the critical points, in other words, the x-intercepts of the derivative function, and then above the x-axis, positive derivative, so original increases. Below the x-axis, negative derivative value, so the original decreases. Put those, and then we get this diagram. And then you can mark maximum, minimum, or neither. And then parts C and D go together, concavity and inflection points. Local maximum or local minimum for the derivative function, -1, positive 1.5, and positive 3. Those are inflection points. So -1, 1.5, and 3. And then the derivative function, this blue function, decreases to -1, increases from -1 to 1.5, decreases from 1.5 to 3, and increases from 3 to infinity. So down, up, down, up. So the original function behaves the same. Concave down, up, down, up. Up is up, down is down. It's easy to remember. Again, practice producing the diagram. And then sketch the graph if interested. And then I gave you more problems like these. Repeat the same problem with the following graph. Let's see. How many critical points do you see? Critical points of the original function. Those correspond to the x-intercepts of the derivative function. There should be 3. X equals to -2, 0, and x equals to 1, 2, 3, 4. Those are the critical points, and those 3 critical points divide the number line in 4 intervals. And then for each interval, you have to answer increasing or decreasing, depending upon whether the derivative is positive or negative, or equivalently, the graph here, the derivative graph, blue graph, is above or below the x-axis. Good luck. As for the concavity, well, how many local extrema do you see? Local minimum here, local maximum here, local minimum here. So the derivative function decreases, increase, decrease, increase. So the original function is concave down, concave up, concave down, and concave up at these x-coordinate values, which are inflection points. Repeat the same problem with the following graph. This time we have this horizontal asymptote here, horizontal asymptote getting close to 0. So it has only one critical point right here, x equal to 0. That's the only point where we have touching. Here it's asymptotic, so not exactly getting to 0, even though it gets very, very close to 0. And then this one here, let's see, local maximum, local minimum, neither. Which is it? It's going to be neither, because the derivative is always positive. So the original function increases all the way. Here, derivative is getting very close to 0, so the original function has sloped very close to 0. So you're going to get a horizontal asymptote here to the left and then to the right. And then here we have neither maximum nor minimum. And then we have inflection point x equal to -1 and +1. So the sketch of the graph of the original function is going to be kind of like this. So horizontally asymptotic goes up, and then momentary pause, but keeps on increasing, and then horizontal asymptote like that. and then this thing happens at x equals to 0. And then concavity changes here and there, x equals to -1 and x equals to +1. Nobody cares about the y-coordinate value, so I'm not going to mark y-coordinate. All these are x-coordinate values only. So concave up, concave down, concave up, concave down, like that. And the interesting case here is horizontal asymptote here and there. That's a little bit different. Otherwise, pretty much the same. Here's another graph here. Let's see, we have x-intercept here, here, and then horizontal asymptote there. So it looks like there are two critical points, and those critical numbers, the x-coordinates of the critical numbers, critical points is x equals to 0 here, x equals to -4 here, those two. So less than -4, positive derivative, between x equals to -4 and 0, negative derivative, greater than x equals to 0, x is greater than 0, then positive derivative. So you can answer increasing and decreasing accordingly. And then you can find the nature of the critical points too. Increasing change to decreasing. So that should be local maximum. Right here, decreasing here, increasing there. So there should be local minimum. Do you see that? As for inflection points, how many inflection points are there? How many local extrema do you see for the derivative function? I see two. Local minimum here, local maximum there. So those two are inflection points. Decreasing, so the derivative goes down, the original is concave down, derivative goes up, original is concave up, derivative goes down, so original is concave down, like that. And then you're going to have horizontal asymptote here. So here we go. Original versus derivative, -4 and then 0. Positive derivative, so increasing original. Negative derivative, decreasing original. Positive derivative, increasing original. So the graph is going up, down, and up, but not all the way up, as a matter of fact, because of this asymptotic behavior. The sketch of the original function will be kind of like this. Increasing is the maximum, decreasing is the minimum. Increasing but asymptotic. And then we have to have x equals to -4 here. You see, positive to negative, so increasing to decreasing, so that's maximum. And then x equals to 0 here. Change from negative to positive for the derivative, so decreasing to increasing for the original. And then to the right, as x gets really, really large, derivative gets very, very close to 0, so gets very flat, horizontal asymptote like this. And then you can expect some inflection point here and there, concavity changes, and then those are going to be related to local minimum and local maximum of the derivative function. So that's going to be -3. And then here, +3. Those are going to be the inflection points. Here's a diagram for part C and D. -3, up to that point is decreasing. The derivative goes down, so original is concave down. From -3 to +3, the blue graph, the derivative is increasing. derivative goes up, so the original is concave up. And then that to infinity, the derivative goes down, so the original is concave down. Here I put x equal to 0 here as if we have a separator, but it's not a separator. The -3 to +3 we have keeps on increasing. The reason I gave you this 0 here is because the second derivative is 0 at x equal to 0 as well, to tell the truth. You see, you have horizontal tangent. Here, horizontal tangent, we have horizontal tangent here as well. But this is not a local maximum or local minimum. This is not a local extremum for the derivative function. So this is not an inflection point. So inflection point corresponds to the local extremum for the derivative function. This one is neither maximum nor minimum for the derivative function. So it's not a critical, it's not an inflection point. Concavity stays positive, stays up, and then the derivative stays increasing, and the second derivative stays non-negative. Positive here, momentarily 0 here, but positive again.